power source to motion. Talks about a system, filters, intake filters, pumps, compressors. These are some of the things we'll look at in the system. Aftercoolers, drivers, receivers, also called reservoirs, pressure regulators, oilers, piping, control valves, directional control valves, flow control valves, actuator orifices, and volumes. So this is basically the stuff we'll look at. We got an old lecture on what consists in a fluid power system. What we're doing now is just working on what? Basically individual components, right? So two main categories of cylinders. We have what we call actuators. We have cylinders and rotary. We have cylinders and rotary actuators. Right? Okay. The difference. So a cylinder creates a linear motion, which is a straight line motion, and a rotary actuator moves in an arc. So cylinders, their stroke is given in a unit, a distant units like feet or inches or whatever like that. And then rotary actuators, the stroke is given in degrees. And then we have a rotary actuator that we call a motor. So motor, even though it's a rotary actuator, it's got its own name, right? So when we use the term rotary actuator, we're talking about an actuator that has a limited stroke. Internally limited stroke. A motor is a rotary actuator that does not have an internally limited stroke. It means we can limit the stroke, but we got to do it external, right? Does that make sense? We got to run the motor until it hits a hard stop or something. That makes sense? So the first one we'll look at is our double acting cylinder. I don't know why the book covers it like this, but what is a double acting cylinder? What do you mean by double acting cylinder? Well, a single acting cylinder can move both ways.
Well, it's powered both ways.
Yeah, so it uses pressure to move, not only extend it, but retract it. Of course, when we talk about extend, we're talking about making the rod go out, right? You understand? And when we're talking about retract, we're talking the rod comes in, which Nancy refers to as push and pull, which makes sense because if you're extending, you're going to be pushing something out of the way, and the other way you're going to be pulling it back. So we use pressure to extend it, we use pressure to retract it. The only problem we have is that our push pressure is going to be greater than our pull pressure, right? Because what?
Because it's minus the rod.
The area of the rod. Because the area of the rod don't apply pressure this way. It's got the pressures on all sides, right? And also the retract speed will be more or less than the extend speed.
Might be faster.
It's going to be faster because it's got lesser area, right? You understand? So it's got less volume to feel. So this is the animation of a double acting cylinder. Now this is a basic symbol. We have symbols. So this would be what we call a simplified symbol. And then we got other symbols that we do depending on what the cylinder actually has in it, right? So what else can we put in here to make it? No, that change the symbol. We can put cushion. We understand cushion. Bumpers don't have a symbol. Cushions do have a symbol. We could make a variable cushion, right? We could also put a magnet on it. And the book doesn't cover the magnet. Then we have what we call double-ended cylinders. Can y'all see how a double-ended cylinder? Double-ended cylinder. So it's got rods coming out both sides. Right? Let's say that. Yes, sir. So here we get work out of both sides of the cylinder. No, and the pressure, the extend and retract pressure would be the same if the rods are the same size, but I've never seen one where the rods would be different. even though they could, if they wanted to, but I've never seen.
We're just asking. Can those cylinders, the rods, be screwed or controlled situation?
What do you mean screw?
Like,
They wouldn't be considered a cylinder, it'd be considered a rotary actuator.
I thought I saw something like that.
You can, yeah, and they do them, but it's not a cylinder, it's a rotary actuator.
Okay.
It's just that we take the rotor and we actually attach the screw. It's usually a motor if it's a multiple turn, but yeah, I mean, it could be a screw type situation. Because the spacing or the slope of we get gain off of screws by the slope, how much the thread slope, right? And how close they're together. So you see some of these screws that have a real high torque rating on them, the threads will be really, really fine and the slope will be narrow, right? It's kind of like an incline, you know, the steeper the incline, the harder it is to get up, and that's basically a screw. It's just the incline is what is wrapped around it. And the longer you make the incline, a single action cylinder. By the way, the book didn't cover this, but I was doing some research on that, and they were talking about single action cylinders where it was pressure return, the actual spring. So it was pressure return. Here it's pressure extend, spring return, right? You understand? But they've also got another one which is pressure retract, spring return. I'm sorry I said that back. Spring extend, pressure return. And the symbol would be the same thing, but the spring would be on the side. Simplified symbols, that's what they got there. Normally we actually draw a little more detail in it, draw the spring. The one on top is load return. So these guys would only be mounted like vertical, right? Understand that? A vertical cylinder. If we got something mounted vertical, then we could let the load return. Like a hydraulic jack that you buy for your car, that is the load return. And a lot of these big piston jacks, these rams, as they call them, separate reel with rods on them, those are usually spring return. Load return. Then we have what they call a ram, and that's a ram is a special cylinder where the rod is basically equal to the bore. These guys have extremely big rods. These guys are the ones that's going to generate a lot of force, right? So these are usually referred to as rams. So the rod size is the same size as the bore. You see some of these big jacks that move houses and stuff like that. You'll see that they're using rams. And then we have the telescoping symbol like so. And of course, the picture I clipped out was one we talked about. You see these lifting things like garbage, dump trucks and stuff like that. And what advantage does that have? Well, these guys have extremely long strokes. Right? So these are some rams. Some telescoping. We've all seen them. Then we talked about getting them up and something happened and get out there on that very end. Are we okay? Two piston cylinders. This is where we actually bring in one flow in the center, and it actually extends it out different ways. The only thing that I could find was the old wheel cylinders that used on brake pad, drum brake. This uses a double piston. Are we okay? Pretty straightforward. Rings, different wipers that's inside the piston. These are just nice to know things. I don't even know if the book gives you an explanation of the different types. Of course, the rings, these are the guys that's actually sealing the pressure in, right? Everybody understand? Are we okay? Not too much. Yeah. That's what rings do, just like the rings on your car. So if we got something in motion, moving to get something in stationary, we got to have something between what's in motion and what's in stationary. So we use bearings, but on something that slides like that, we use rings. Some of them actually call them bearings, but they're actually rings. In pneumatics, we use a lot of rubber. In hydraulics, we use a lot of multiple metal bands that come down because the pressure is so high. Caps. We have basically three types. We have the rod type. Now, I don't think of any of ours as the rod type. I'm not sure if ours is the screw-on type. It looks like they might be welded or pressed. So your rod type and your screw-on type, these would be user repairable, which means you can take them apart and replace the rings on it, right? Okay. A welded type would be non-repairable, but the welded type would be cheaper. Makes sense? So you start thinking non-repairable, usually that means they're going to be cheaper. But in the long run, you'd pay more money up front for the repairable, but it would be cheaper to repair. So these three, the rod type, the screw-on type where the caps are screwed on, and then the welded on or pressed on. Are we okay?
Yeah. What's the purpose of the cap again? Like a cushion?
Okay, what is the purpose of a cap on a managed? What's the purpose on the cap on a coat?
Oh, okay. That kind of cap.
That's how it is. So you have the cylinder, and then you got something that goes on both ends. Usually, if it's a single rod cylinder, they call the end away from the caps. But normally, this guy right here, most people call this the head, and then this one on the back, they call this the cap. And that's just terminology, but that's what the caps. You gotta seal that cylinder up. So what are you gonna put on there? You're gonna put a cap.
Okay, so the way they out there, you maybe say I can attach something else onto the end of it.
Well,
You maybe do have to do work a certain time.
Well, not have to do work, but you're gonna have to attach these cylinders on something, right? Over here, we're attaching ours onto a wall, but then you gotta take the output of that cylinder, and it's either gonna push something or it's gonna be attached. So one of the things they cover in the book, and they do a real good job on it, the different ways you can mount these. So these cylinders are got to attach to something, right? And some of y'all have learned, and that's another thing that I need to make sure I teach something. Since Nancy's not teaching any classes anymore, this might turn into one of my primary classes. But so when we mount our cylinders up there, we got to get on there and screw them down. Some of y'all didn't do that, and every time what would happen, you know, it would move. So y'all got to get used to tighten it. Not, but over here you don't want to over tighten it, right? I threw this in. This is not covered in your book, but this is becoming very popular. In fact, every piston that we have, every cylinder we have over there is magnetic. So literally, they have a magnet mounted on as part of the piston. And then ours, since we're using pneumatics, the actual shell for the cylinder is aluminum. Now, what aluminum does, it does not block magnetic fields. Magnetic fields move the aluminum like it's not in the magnet. So now we can use that magnet to do what? To sense position. Just about every cylinder we have over on our two manufacturing lines over there use pneumatic pistons. And then we mount things over there. So we have two switches over there, valves that are magnetically activated. So we can actually mount them on the end. Use those valves. Ours takes that position and converts it over to an electrical signal where the programmable logic controller will know whether the cylinder is fully extended or fully retracted. You don't know where it's at between there, but you don't really need to know that, right? You understand? So with the PLC, so that way the PLC can run just as fast as we can run it, because instead of trying to use a timer to say, okay, before I retract that, I gotta make sure it's fully extended. We know it's what. We know it's fully extended. So we got 2 of them over there. Should be part of your input. So when y'all start designing stuff, y'all might think about using those. Nobody's used them yet. Mounting, we have different ways we can mount the thing. So this is in the book 4.6. And it's pretty, they give pretty good drawings here. These are all rod type cylinders. So tie rod extended, y'all understand that one? That makes sense. Then we have what they call a centerline lug. You'll see how they do that. Yes or no? So these actually have threaded holes right here, right down the center line. This is called head. So now we know. So this has a plate out here, and this is where we'd actually mount this one. Head flange mounting. Head flange square, head flange rectangular. We okay? Cap end. So this is where the head and the cap comes into play. So notice this is the mounting plate that's on the cap end, and then square and rectangular. These are pretty straightforward, right? Okay. So here we're going to mount. So which one are we using? Sunlight, yes, that's pretty dang close to what we're using. I hadn't seen actually how it's mounted, but our actually base mount is centerline. Then we can move over and actually, side lugs. Can you see them right here? Yes or no? Side end angle, side end lug, side tapped holes. Are we okay? Now I'm not sure. I have to go over and get one and see actually how the cylinder is mounted on that thing. It looks like it's just mounted on the compression side of the thing. So these are all the ones that cover in the textbook, right? Pivot cylinder. Oh yeah, no, it's not. So here's what we call a cap trunnion. So it's got these 2 bars sticking out the side, and then we'd put these on bearings. And this gives the ability for the whole cylinder to do that, right? You see that all the time, especially on earth moving equipment and stuff like that, where the thing's got to move, and you see the whole cylinder moves with it. Intermediate trunnion. So this has got the rod sticking out the side, cap fixed clevis. And then what's this one? Head trunnion. Are we okay? I don't know if the book covers how we connect the rod. We have different ways we can actually connect the rod on. And I don't know what they're talking about here. What does this book say? 4.9. What does it talk about in 4.9? I have no idea. What does it say when it writes it up? What does the book say about? For example, suppose you want to use low. This will low across 400 pound force. The air pressure is main outlet too large. Are not too large enough? Large enough they're large enough.
Large. Yeah. Large.
Oh, they got an extra two. I don't know where they come 400. It says 400 pounds.
No, wow, 400 pound torque.
There's a lot of math involved here. We just don't talk. So look, the pound is 4,000. The weight is trying to move is 4,000 pounds. Why don't it need to create 4,000 pounds of force to move? No, I'm talking about I'm looking at the diagram. Huh? No, well they said the force is 400 pounds. Well, we even do this, you know. I can slide things on the floor that I can't pick up. Because here you're not supporting all the weight, right? You understand? So there's a lot of math involved on how much force is actually required to move the load. So 4,000 pounds would be if it's trying to lift that sucker what? Vertically, right? You understand? And then the closer I get to this, the less weight we're going to have to push. And there's math as far as how to calculate the incline plus the friction of what you're trying to slide across before you actually can get it. So when we talk about 4,000 pounds, and of course if I was pushing it downhill, it would actually start subtracting, right? You don't understand that. But here, if we're going flat, flat would be the less force required pushing it flat, right? You understand? And then when I start inclining, the amount of force required would keep it going up until I got what? Totally vertical. Then I would have to have at least 4,000 pounds of force. Above 4,000 pounds of force. You gotta understand, if I get 4,000 pounds of force, I'm not gonna move a 4,000 pound weight. Available, I'm not gonna move a 4,000 pound weight, right? Because that would say we got absolutely no friction in the cylinder itself. So they say at least 25% more pressure available. 25% more pressure available than the biggest force you're going to move. Cushions. We talked quite extensively about cushions. So we know the difference between cushions and bumpers now, right? So bumpers, what would a bumper be? Just a rubber mat, basically, inside the caps, inside the head, inside the caps. That's all a bumper is. A cushion, by the way, is actually a what? Yeah, what we do is we deliberately control the exhaust or the extend when it gets to the end, right? Okay. And then we come up here and add these little check valves where we control that backflow out of the cushion back into where it's supposed to be. Then that means the cushions are variable. So we come over here and we add something else to our symbol if we're going to draw a detail symbol. So this would be a simplified symbol for a single action symbol. We don't even draw a cap. Then we come over here, and I normally don't do that. Normally I do a simplified version like that. Normally, if it does this, we go ahead and add that, but that's a little different, right? Then what we do when we move on up to these more detailed, we'll start doing this, right? You understand? And then if we got cushions, we'll come over here and put this on here. Everybody okay? Then we come over and do that. It says it's what? Variable. And then we come over here and put this in here. It means it's what? It means it's got a magnet. So this would be the true symbol, detailed symbol for all the cylinders that we have. And that little U is a universal indicator, by the way, for magnets. It's the SI standard. So we'll get into sensors. We don't talk about sensors in this class, but that's the symbol that for a magnet. So if you've ever seen it. So this is a real good diagram. I don't think that this come out of y'all's book. This is really good. As far as how the actual cushions work. Well, I don't know where I got it at. This must have came out of the hydraulic slides. Controlling the speed of the actuator. The time a cylinder will fully extend or retract is determined by the volume of the fluid needed by the cylinder per stroke and the flow rate of the fluid. Go ahead. Mm-hmm. Sure. This should be up on the, it's fine. Don't it kind of angle it?
I took mine just because I didn't work. I understood what it said.
The time it takes a cylinder to fully extend or retract is determined by the volume of the fluid needed by the cylinder per stroke and the rate of the flow. Where area is in square inches, L is the length of the stroke, and T is the time in seconds. So this is not extremely difficult. So when you calculate the area and you multiply it times the length, that's going to give you the volume. There you go. Are we okay? Is this one in the book? Huh? I know it's a slide. The volume of the cylinder cannot be changed. A double-acting cylinder with a rod will retract faster than it extends. Variable displacement rotary actuator, the volume can be changed. Most cylinders we can't change the volume of a cylinder. Some of your rotary actuators we can actually change the volume, the displacement. I've never seen one. I've never seen one. Now we can do some strange things that kind of simulates that. We can limit the stroke. So if you limit the stroke, you limit the volume. So I could literally put a hard stop out there. And I might have a 12-inch rod, but I always stop it at 9 inches. Well, when I stop it at 9 inches, but I'm going to have to do that externally, then we would limit the volume. But we're doing it not with the cylinder itself, we're doing it externally. Variable displacement actuators, you actually change the displacement. So when we get into an actuator, we get into something that rotates. We start talking about displacement and not volume, especially rotary actuators, especially motors. Because motors, we get into different situations where, so we talk about the size of an engine, like 2.4 liter or something like that. What are they talking about? What are they talking about? Y'all talking about, huh?
All.
I don't know. Y'all.
Anytime you talk about liters, you talk about volume.
Right, but what are they talking about on your engine? What are they talking about? Oh, 2.4 liter engine. So what are they talking about? They're talking about the displacement of the motor. I mean, what does that mean?
That got to do with how much the gas is used.
Well, not gas.
Oh, fuel.
Oh.
Okay,
Well, it definitely deals with cylinder size, but you got 4 or 5 or 8 of them out there, so what do they talk about?
Air.
That's how much air it can move through that motor in one revolution.
The motor, and that's how much air.
That's the displacement of a motor, so a motor gets
That's what a turbo
displacement. Yeah. So you move the air through there faster. So that's what the displacement. So when they talk about a 350 cubic inch engine, that's not the size of the engine. That's basically how much air that motor can move through that engine in one revolution. That's exactly what it is. So that's when we start talking about motors, we start talking about displacement. That's how fast a motor determines the rotary is how much displacement you have. Right? Does that make sense? You know that? You didn't know that?
Never knew it in the terms. Never thought about it like that.
So that's what happens. So the bigger the pistons, the more air it moves. We got 1 or 2 options. We can make the pistons bigger and use less pistons, right? So you got some 4-cylinder engines that can displace more than some 8-cylinder.
That's what Ford's on.
But they're big, huh?
That's what Ford's on. The Echo that they got.
So you real big cylinder.
No, you know they're saying.
Well, what they'll do is they'll actually cut off one cylinder.
They're saying.
The valves are controlled electronically. They'll open up both the exhausts and the valves. So that sucker's in there just bouncing back and forth.
They'll try to send the truck east west up and down that you go through the engine. V6 got more power than my V8.
They're pushing more. Don't lose them. That's more to do it. So put there to pack.
Yeah, turbo would move the air faster. So good. So I taught y'all something. So usually rotary actuators, we deal with displacement. This is also true on motors, fluid powered motors. It's how much air we can push through that motor or how much liquid we can get out of a pump, right? Deal with how much displacement you have. These are estimated speeds. And these are all, when we get into pneumatics, speeds are very, very complicated to be exactly precise. And this is one advantage that hydraulics has over pneumatics, is that hydraulics is really spongy. It's trying to uncompress all the time, and then it's got to recompress. And so it's pretty hard to deal with precise speeds with pneumatics. So if I'm not dealing with some real high precision, what advantage does pneumatics have over hydraulics? Yeah, the system is usually cheaper. I mean, good gracious, we can use plastic piping instead of steel piping. We can do, the valves are not going to be near as expensive. It's going to be very clean. It's going to be very safe, right? You understand? If we spring a leak in a pneumatic system, we lose pressure. It might not do what we're going to do, but it's not going to come out there. They've got situations, guys, where guys have lost arms. Not from cutting with hydraulics, it's getting hydraulic fluid shot into them like I found out somebody was telling me that. If you're ever in the military, anybody in the military? They give shots. How do they give shots? How do they give shots? Shoot them. Yeah, they have air. They don't use needles. They have the high pressure needles, and they put a big old thing on the top. And they literally shoot that into your arm with nothing but air pressure. Well, we've had people that's lost arms because they get into a high pressure hydraulic system. It's got a little tiny leak and it gets that hydraulic fluid in their muscles. And it just rots. Like it starts turning black and they don't know what's happened by the time they get to the doctor. There's really nothing they can do. So be real careful around high pressure hydraulic systems. Like I said, the planes that I worked on, they ran those pumps at 3,000 psi on those airplanes that I was working on. You didn't want to fool around with a leak on those things. You get those little hairline leaks, that we get all the time. So what does it say here? It says estimate cylinder speed, figure belows are in inches per second. So over on the left we have the bore size, and there's so much that causes us to lose pressure in the system. So anytime we flow through something, we're going to lose pressure. If we lose pressure, we lose force and we lose speed, right? That makes sense. So what determines, and this is why you got to really, we don't teach the engineer, but the people who really engineer fluid power, they got to consider the size of the piping. They got to consider the size of the orifices in all their valves, everything they've got to consider, because not only they're trying to move something, they're trying to move it at a certain speed. So it's a pretty good deal of math. All we can do here is just approximation. Actual valve orifice sizes, bore sizes of the cylinder, then basically, and this is as where the force required is 50% available for 80 to 100 psi. So what they've done to come up with these approximations is they've actually decreased the force or pressure available. They have a 50% overhead, right? You know, all the math that I've looked when they calculate the speed, they're talking about if you really want to make something move, then you're going to overbuild everything by 50%. The directional valve's internal flow is equal to the porting and unlimited air supply. So you got to consider the flow rate of your power source. Acceleration distance is assumed to be relatively short. So the further you got to move something, we got more things that come into play. Stroke based on sufficiently long stroke. So it says figure below is in inches per second. So that means if we got a bore of our orifices are 3/32 of an inch, our bore is 1 inch, we could probably move about 6 inches per second if we allow for a 50% error, right? That makes sense. In pneumatics is extremely. Controlling the speed of the action, since the volume of the actuator cannot be changed. Okay, did I go backwards? The speed of a cylinder is controlled by the flow rate of the fluid actually entering the cylinder and the area of the cylinder. The speed of the motor of a rotary actuator is controlled by the fluid flow rate entering the motor and the motor's displacement. Pneumatic flow rates are usually given in standard cubic feet per minute. And what is standard cubic feet per minute? That sounds like a good test question. So you can go anywhere and you start shopping for compressors.
Standard, you said
But what does it mean?
it must be,
We've talked about this several times already.
That has to be, US,
It's U.S. customary, yeah.
yeah. So they got to be,
Well, overseas they do the same thing. They have standard liters per minute. It's just so they use SLM, we use SCFM.
so it'd be 12 times twice. Bottom.
Yeah, well, squared, feet squared. But but standard, we need to understand what standard cubic feet per minute is. That means I go out and buy a compressor and it's rated at 9.9 CSCM. Does that mean that's what I'm going to get? So what determines the pressure, which would be also the flow rate of air?
Are you referring to?
So how do these things work? Where does the pressure come? What is the pump? Does the pump actually create the pressure? Well, it creates the flow, and then when we work to get something, it has pressure. So we're constantly seeing pressure multiplication all the time. What makes a pump? What makes a pump pump? Does a pump? All the pump does is create low pressure. What pushes the pressure, pushes the fluid into the pump? What for?
Well, compressor.
What compressors or pumps or anything? What actually pushes it into? So to get anything to move, we got to have a difference of potential or difference of pressure, right? So all the pump does is it creates low pressure. Where does the high pressure come from?
First.
Right?
Not gravity. It's atmospheric pressure. That 14.7 psi is pushing on everything, right? In all directions, bottoms, tops, and everything. So if I got a big old thing of liquid out there, it's got a surface on it. 14.7 psi is pushing down. The pump is over there creating a low pressure, and what does it do? It sucks it into. So when I started talking about standard cubic feet per minute, what's pushing it into the compressor? Atmospheric pressure. So it's got to have something to do with atmospheric pressure. Atmospheric pressure varies with amplitude. So we got two things that vary the pressure. We got the temperature and we've got the altitude. Okay, you understand. So that means when I talk about standard cubic feet per minute, it's got to be at a certain altitude and it's got to be at a certain temperature. What altitude do you think they use? Sea level. The mean value of sea level. That varies too. So what they've done is they've measured this all over the place and they've come up with an average, and the average is 14.69 something, but we say 14.7 is the mean or the average. And what temperature? I think it's 60 degrees. Because we know if temperature goes up, pressure goes up. If temperature goes down, pressure goes down. That's one of our main laws, right? You know, it varies directly with temperature. So when they say standard cubic feet per minute, they can't just say it because it's going to vary. So I mean, a compressor rated at 69.9 cubic feet per minute, the closer I get to sea level, the more that's going to be true. The higher I get up, the less that's going to be true. So we have what we call ACFM. What's ACFM? Actual. How would you come up with ACFM? You would have to actually measure it, right? You understand? You could look up and, you could look it up and get what the average is, but your compressor still is going to vary a little bit. We have high pressure system and low pressure system. Well, that's what they talk about, high pressure and low pressure. So cold air creates what? High pressure. Heat creates what? Low pressure. So now we know, we talk about high pressure and low pressure in weather all the time. There's basically a low pressure and a high pressure all the time somewhere, right? Even in the summer. You have 90 degrees. Somewhere it's going to be 89 and somewhere it's going to be 92, and so you have a low pressure and high pressure. And the air flows from high pressure, low pressure. So when we rate a compressor, that's all they can do is just give us a standard. So your compressors are going to be rated standard cubic feet per minute, right? All speed calculations are estimated due to losses in the system caused by piping, fitting, porting, through valves. So everything that liquid or that fluid has got to flow through to get from the power source to your actuator can cause fluid loss. Pressure loss. If we lose pressure, we're going to lose speed, right? You understand that? To accurately calculate actuator speed, actual inlet flow rates must be used. If we know the actual flow rate into the cylinder, then we can do a really good job. Unfortunately, we don't even know what the flow rate is. We don't know the flow rate of the compressor. We use extremely small piping, so we're going to impede our flow rate already. Y'all see that over there already, right? You see our pressure regulator actually drops below what it's regulating because we're losing what? Pressure in the system. So here's our formulas. And I'm not sure if these are covered in the textbook. hydraulic. So we got to take gallons per minute and convert it over to a standard unit, which would be cubic inches per second. So this is where the 231 and the 28.8. A lot of people for pneumatics they just use 29. You'll see that in a lot of formulas. You say, where did that come from? Where did that come from? Well, it's the conversion factor going from what? Gallons per minute over to cubic inches per second. So now we calculate that over, then basically the formulas are the same. So you notice the formulas are the same, except in hydraulics I'm going to use 231, in pneumatics I'm going to use 29. I should have went back and changed it to 29 because using 28.8 on speed is basically a waste of time. So most of your formulas you'll look at use 29 instead of 28.8. So that's going to take your cubic gallons per minute and convert it over to cubic inches per second. So hydraulic velocity in inches per minute. What if I wanted to get feet per minute? Well, I just drop the foot off the bottom, right? I mean the 12 off the bottom. So it's the same formula. It's flow divided by area. Are we okay? Any questions? What if I could do a little formula to copy into the textbook? Why? Because you have the test in your open book. Are these going to be exact? No, these are approximations, right? Let's take a break. Yeah, we're fine. I'll come back in here. Let's see how much we got to do. I think this lecture is about full. No, it's not. CV, most of the stuff we already looked at. Pressure. You have a pressure problem like that. Yes. We're going to lose force instantly. And that's why we did all those check valves, which is a really good example. So anytime we put flow control in there, you're going to lose two things. It's going to develop a pressure drop, which is going to reduce your force, and of course, you're going to reduce your speed, which is what we're using for. This is why we got to make sure that we have plenty of pressure available. They say about 50%. Good rule of thumb is 50% more pressure available than what you actually need. And these are all hydraulic. These are not going to be in the book. So any questions? So we'll go up here. We'll look at some of these valves. We'll talk about something that we use in the United States. It's called the flow coefficient, or the CD rating of a valve. So the only thing that would change between a hydraulic CD rating would be, instead of using 29, 231, right? But this is just a number. Instead of giving you the size, they give you the CD rating of the valve, and it's basically gives us a coefficient of how fast the fluid can go through the valve. So when I go through a directional control valve, we're going to lose what? Pressure. If you lose pressure, we're going to lose force and speed. So piping, we lose pressure through piping. Directional control valves, we use lose pressure through directional control valves, and of course flow control valves. We lose pressure through those. Anytime we lose pressure, we lose two things: we lose force, and we lose what? Speed. Everybody okay? Okay, I might have to run off some lamps. Let's go ahead and